Hello everyone, my name is Mohammed Abdurrahman. I'm a PhD student in IIT Guwahati. Today I'm going to presenting data-driven end-to-end equivalence checking of high-level synthesis. This is the paper published in ISQD 2022. This is my presentation outline. Introduction. High-level synthesis is the process of translating an abstract behavioral specification, usually in C or C++, into register transfer level. So when you see this high-level synthesis process passes different phases. The first phase is pre-processing, which transforms the input description into an internal representation, and also virus compiler optimization will be done in this phase. The next phase is scheduling phase, which assigns time step to the operation without violating data dependencies among the operations. Then after that, allocation and binding phase. This phase determines the selection of the types of hardware components like functional unit and register, and binds the operation to the functional unit and variables to registers. Finally, data path and control path generation phase, which the interconnection among the functional unit and the registers are determined in this phase, and also create a control FSM. The complexity of hardware design increases rapidly. Why this high-level synthesis is an attractive choice for the design house? The first reason is design at a higher abstraction level, means shorter design cycles. Specification is simpler at higher abstraction level. Specification in C or C++ reduce the complexity of a design 10 times compared to RTL design, and it is easy to explore design space with high-level synthesis. Motivation, high-level synthesis is a complex translation process. The semantic gap between the C and RTL is the primary challenge in RTL to C equivalent checking. High-level synthesis are not bug-free. Recently, many bugs are identified in some high-level synthesis tools like Vivadio HLS, Bamboo. RTL to C translation validation of high-level synthesis is not well established yet. It is an open problem. Then the phase-wise verification of high-level synthesis node is full, since it needs the intermediate information from the high-level synthesis. So with the above motivation, our work will aim to achieve the following objective: develop a C2RT equivalent checking method called DEEQ to prove the correctness of the high-level synthesis generated RTL with respect to its input C code. Then we use some techniques like merging compatible trace and data-driven approach to improve the performance of our tool and to make the process tool independent. So our equivalent checking flow has two phases actually. The first phase is we abstract out high-level C like behavior called RTLC from the RTL. In this case, we utilize the method presented in this paper. In the next phase, equivalent checking between inputs and RTLC is carried out. So there are many challenges in C to RTL equivalent checking. The first one is direct trace level comparison is not possible due to the semantic gap between the C and RTL. To address this challenge, we abstract out a high level C like behavior called RTLC from the RTL. The other challenge is the number of traces is also large in most cases. So to address this challenge, we identify compatible traces which have the same output within a behavior and merge them into one. Then we use a data-driven approach to find the corresponding of trace between two behaviors. So after we have done that, then the next step will be modeling all behaviors into FCMD. So the C program and the RTLC program are automatically converted into an FCMD model. So we have two FCMD, C FCMD and RTL FCMD. For example, in this case, this is a C behavior. This C behavior will be converted into FCMD. So in this case, as you can see, this is a reset state. If n is greater than or equal to I value, X value, and Y value will be initialized. Then the for loop will be evaluated. If I is less than or equal to 10, X which is equal to 5, Y will be incremented by 1. Then this process will be continued until this condition is false. If this condition is false, then output will be X plus Y. Then this will come again to the reset state. Then this process will continue until the condition is false. Likewise, we can also model RTL FCMD like this. So equivalence problem formulation. A trace of an FCMD is a finite work from the reset state Q0 to itself, and Q0 should not occur in between. There are two things: condition of execution and data transformation. These two things which are passed to compare whether two traces are equivalent or not. So this condition of execution, C power of a trace power, is a large expression over I which must be satisfied by the initial data state in order to traverse power. Data transformation of S power of a trace power over I is an ordered tuple. Each of an algebraic expression over I says that expression ij represents the value of the output oj after execution of the trace in terms of input variables. So if you say two traces are equivalent, if only if their respective condition of execution and data transformation must be equivalent. If this condition is satisfied, then we can say that these two traces are equivalent. So when you see the equivalence checking between C and RTL, our algorithm will follow this one. We have actually two phases, phase 1 and phase 2. We have C input and RTL, which is generated by the behavioural HLS. Then first we are going to convert this RTL into the equivalent RTLC. So this is phase 1. Actually, we utilize, as I have said earlier, we utilize this method to convert RTL to RTLC. Then once we have this one, we convert both into FCMD. After converting into FCMD, then we are going to identify all traces in both behaviors. Then next step, merging compatible traces. If traces have the same output in a behavior, then we can merge them into one. Then after that, find potential corresponding traces. Then if all traces are merged, if they are one-to-one trace in both behavior, then we can check one-to-one equivalent checking. If that's not possible, then checking one-to-many equivalent. Then finally, our algorithm will generate either equivalent or may not equivalent. So let us see one by one. Generate all traces in both behaviors. So actually, we use a CLI for this purpose. Then the loops are unrolled. Then as you can see in this example, there are two traces there. This trace one and the other trace is this one. Like this, we can generate all traces in both behaviors. Then after that, we are merging. The next step will be merging compatible traces. To improve performance, traces which have the same output expression in each behavior are merged. So two traces, power and power one, they have their respective condition of execution and data transformation. Then if they are compatible, if only if their data transformation is equivalent. So after merging, then the new trace will be, it has its own condition of execution and data transformation. The condition of execution will be the union of the both traces, power 0 and power 1. But data transformation, we can take either of one because they are the same. For example, in this example, here, beta 2, its data transformation is C times D. Then trace B1 before, its data transformation is C times D. So we can merge these two traces into one. Then we can get the condition of execution will be the union of node C2 and node C1. Data transformation, we can take either of one of them. Then after that, we are going to find potential corresponding traces. A data-driven approach is taken to find the potential corresponding traces between T0 and T1. For example, in this case, assume this alpha 1 actually clearly give us the inputs values. So if C1 which is equal to 1, C2 which is equal to 1, then the trace will be this alpha 1 will be our trace. Then the same value of C1 and C2 will be applied in this RTLC code, RTL FCMD. Then in this case, then we will get beta 1, beta 2 will be the corresponding trace for alpha 1 because C1 which is equal to 1, C2 which is equal to 2. Like this, we can find all the corresponding traces between all the corresponding traces for all traces. So checking one-to-one equivalent checking. So first we are copying combination trace of T0 into copy 1, T1 into copy T1. So in our approach, we first identify the one-to-one equivalence among the traces of T0 and T1 in the while loop. So as you can see here, first we are going to find power 0, select the trace of T0. Then we are going to get the test case for this one. Then we are applying the same test case for T1 to find the corresponding trace, power 0 and power 1. A potential corresponding test pair are equivalent if their respective condition of execution and data transformation are equivalent. If they are equivalent, then we can say that these two traces are equivalent. Then we are going to remove powder from copy T0, T1 from copy T1. If the condition of execution, here in this case, if the condition of execution matches, but the data transformation are not equivalent, then we report an equivalence. In this case, at the end of the while loop, the trace for which one-to-one equivalence cannot be shown remains in copy 0 and copy T1 respectively. The next step is checking one-to-many equivalence checking. For each trace pi 0, in this case, pi 0 in copy 0, we identify the trace in the interactive manner in copy 1. That overlap condition with pi 0. Here, as you can see, this is the overlap condition in there. If the output of any of such traces are not equivalent here, if they are not equivalent with pi 0, we report non-equivalence for non-equivalent. Then we are going to report non-equivalence. So for each trace pi 0 in copy 0, we identify all traces in copy 1. We have the same data transformation of pi 0. So in this case, the union of, this is the union. So the union of the condition of execution of all such traces must be equivalent to the condition execution of pi 0. Then when you see the correctness, the set of pi 0 has a finite number of traces because while loops are always terminate, for loop also always terminate, then algorithm is always terminate. So the soundness, the control is reached here only when the equivalence of all the traces pi 0 and pi are formally proven using an SMT solver. So here in 28, if it's a equivalent, means whenever all the T0 and T1 are formally proven by using an SMT solver. So that's why we say our algorithm is sound. So when you see the experiment result, DEEQ is implemented in Python. behavioural HLS is used to generate Verilog RTL. We use also p-Verilog parser to extract abstract syntax tree from the Verilog. So in this example, let us look at the traces, number of traces. So in this case, for input C, number of traces 3. For this one, number of traces 4 after merging 3, 3. This one is for 4 after merging 3, 3. 12, 23, 2, this one. But when you see the FD after merging, even we could not find the same number of traces in both behaviors. Then we have checked also the equivalency. So our method successfully checked the equivalency of all traces in both behaviors. Then when you see the time also, this is not much. Then we have also checked the non-equivalency after adding some incorrect data into each test cases. So result analysis for find mean, there are many compatible traces found since one of the 8 input will be the minimum. As a result, 128 traces are merged into only 8 traces. Parker and Waka example, the number of traces become the same after compatible traces. But when you see the FED, then after merging also we have got a different number of traces. So in this case, we are going to use one-to-many equivalent checking technique. Tested on a recent bug report in Vivado HLS tools, our tool can detect the report bug in Vivado HLS also. None of the existing technique can handle the scenario of equivalence. So we also compare our tool with others, for example, V2C, but we found that V2C generates incorrect C code from the Verilog generated by Vivado HLS. There is also one VTV, is the closest to our work. VTV fails to show the equivalence when the number of traces is not the same. C and corresponding RTL. So in this example, this VTV will not work when this one is for Waka, for Parker, and for DFD. So let us discuss question 1. Numerous studies have investigated on verification of high-level synthesis in past decades. That this problem is still relevant? Yes. Scheduling verification, allocation and binding verification, database and control verification, all these needs, they are phase-wise verification, so we cannot use them for in-between verification. The other one is in-between verification. This also needs intermediate information from the high-level synthesis tools, which our tool does not require. Why the database equivalence checking commonly used for scheduling verification cannot be applied here? Because The idea in this is, in this one, the idea is to insert a cut point in the FCMD to break it into a final state of paths such that any of trace can be represented by concatenation of the paths from that set. All loops of the behavior must be cut by a cut point in this technique. The BPEC method either extend paths or propagate mismatches values to the subsequent paths when equivalence of the paths cannot be shown. So the path extension or value propagation may be carried out till the reset state in the worst case. Therefore, all the BPEC methods have exponential time complexity in the worst case. The other reason is there are no common variables among C and RTL. So that's why we are not we cannot apply here. The other question is the assumption to have a static loop bound in the proposed approach a strong one? Yes, because high-level synthesis tools do not support dynamic memory allocation. The dynamic arrays are replaced with static arrays. So the loops are used for array implementation in a program. So therefore, most of the loops in the high-level synthesis application have a static bound. So when we come to the conclusion, we have proposed RTL2C translation validation framework for verification high-level results. The innovative part of our work is to improve the efficiency of equivalence checking R, extraction of C-like behaviors from the RTL to reduce the semantic gap between C and RTL, merging compatible traces within a behavior, and we are using a data-driven approach to find the corresponding traces. The equivalence of potential equivalence traces are then formally proved using an SMT solver. We have also tested on a recent bug reported in behavioural HLS tool. Future to use technique like invariant sketching and query decomposition of the SMT formula. So thank you. This is our address. Thank you very much.